All right, so this is the second part of the recorder. Turn on, get onto the internet. Okay, DDR. Specification. Oh, it's actually the same page. I forgot one thing, timing. That's it. There we go. That's the same article that I was reading on the phone. So these are the numbers, okay? 99925, 99924, and we want to refer to figure 1, which is, so they're talking about these numbers here. Okay, so these numbers are respectively CL, TRCD, TRP, TRAS, and CMD. The rest of the article, so moving on to the next page. So let's see if you guys can relate what we have just learned to this. Okay, CL. Okay, give me just magnify a little bit. CAS latency, known as access time, is the most important part. It is the first of the series of numbers. It's the delay time between the moment a memory controller tells the memory module to access a particular memory column on the RAM module and the moment the data from the given array location is available on the module's output pins. So this is the delay for a read operation. Okay? Okay, let's go back to our memory chip here, which is a very simplified version of what we talked about. And of course it's not there because I just restarted the computer. Go ahead and restart that too. So, okay, let's go ahead and do a read operation this time. And okay, to do a read operation, let's access this particular location. And I'm going to change the location first so that we can actually read that location back. So that would be 08, which is this location. We'll change it to AE, okay, in hexadecimal. And then we'll close the window. So we want to access this location. I want to read that location. Let's see how much work we have to do. This is location 108. I'm going to simplify and speed up the process a little bit here. So 108 is a 1 here and a 1 over here. So I'm now addressing the right location. I have to change LD to a read operation, so LD has to be a 1. And that way it is now driving the output, okay? So you see the changes as instantaneous changes on the screen, but when you are looking at the changes through an oscilloscope and you're probing a motherboard, it takes a certain amount of time. That, what we just did, from the moment we change every signal on the address bus to the time the data actually appear on the data bus, that's your CAS. That's your actual latency time. Okay? So faster memory works. The more money you pay, the shorter that time is. And that way you can clock data out of your memory quicker. Okay? Let's look at some of the other numbers. As long as it is not really difficult, we can do that. Okay, TRCED stands for row address to column address delay time. That's specific to dynamic RAM, so we're going to pass that one. Pre-charge. Okay, so the CAS is really the most important part. It doesn't have any write delay here. Okay. All right. So I'm hoping you still find a correlation between the RAM speed specification of stuff that you can actually buy off the shelf and this particular picture. This is a really, really simplified picture. Are there any questions about this? No questions? What about DDR3, DDR4? How does it work? Okay, so if you look at the clock signal here, let me just redraw the clock line, okay? This is the memory clock, which goes at a certain rate. Just go tick, 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 tick. Okay, so tick, 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 tick. Okay, we went from only using the rising edge to using both the rising edge and the falling edge. This is double rate, okay? Because it's doubling the amount of data that can be transferred. Now, it can also use the hidden, there's no edge here, but if the memory and the processor, if they agree on the timing, they can both agree and go like, oh, midway between the rising edge and the falling edge, we'll also have one data exchange at that time. That's how you can fit more data transfer between the clocks, between the edges. Are we doing okay so far with this picture?
So the fourth is just going to be around.
Right, so for each clock cycle, you can now have 4 memory transfer instead of 1. But this only happens in burst mode. In other words, you set up the start address, you tell the memory chip and say, we are going into quote unquote burst mode, and this is the number of bytes we're going to transfer, or this is the number of transfers that's going to happen. So now the processor and the RAM chip, they're in agreement and go like, okay, we're going into burst mode for 64 locations, or whatever number. So then you just perform 64 transfers in either direction. But timing becomes extremely important, because if one is off a little bit, then it's going to off and it's not going to work. The whole thing will fall apart because there's really no actual hard synchronization between the two. It's not like the memory chip or the processor says, hey, memory chip, are you ready? The memory chip says, yes, I'm ready, and then you do the operation. That's full handshaking, which is really nice in terms of making sure the transfer happens the way it's supposed to, but that takes way too much time. This has no agreement. It's really just keeping track of the timing and using implicit timing in between to give you the extra transfers. Okay, so that's kind of in a nutshell how DDR works. Yep.
So this rate of data transfer can also depend on the frequency. Like some memories have like 800 megahertz.
Right. The 800 refers to the actual clock frequency. So when you look at 800 megahertz as a clock frequency, it's basically saying, okay, the time between 2 rising edges, okay, that's the period, or I should say, this is 8 divided by 800 megahertz. Okay, this is the amount of time. But within this amount of time, there can be multiple transfers. Okay, so you see one number as the clock frequency, and then you see the other one as number of transfers per second. And that's why the number of transfers per second is almost always a power of 2 times the actual clock frequency. And that depends on whether you're talking about DDR2, DDR3, or DDR4. And then the width of transfer is also really wide, okay, depending on whether you populate only 2 out of the 4 banks of the motherboard or all 4 banks of the motherboard, because you can actually double the width of the transfers too. All right. Are there any questions about this part? Okay, next question, okay? This is all mechanical stuff. But why? Why are we going through all this trouble, going through using all these tricks to improve the number of bytes that we can transfer between memory and the processor?
To make it faster.
To make it go faster, but why don't we speed up other things, like increase the number of cores inside a processor? If I give you a 16-core processor, but without improving the memory bus, what's going to happen?
Bottleneck.
You have a severe bottleneck, okay? You will have, okay, I said 16 cores, right? So you will end up probably with 12 cores doing this all day long, twiddling the thumbs, like that. It's like, I'm waiting for the content, waiting for the next instruction. A comparison is Okay, if this classroom is the processor, okay, and each one of you is a core, okay, we are basically saying in order to get the next instruction for any one of you to execute, we can send one person to the library to fetch one page of instruction for that one person. Okay, now we have about, I would say about 35 students right now in this classroom. So that means, only one person gets to do any work. The other 34 is waiting for the turn to go to the library to get the instruction. Okay? And it really is that long to get to the library, to get memory, because it's a very slow operation. Now, don't forget, both because of von Neumann, okay, what is his contribution to computer science?
Multitasking.
Not multitasking. Before von Neumann, what do computers look like?
They were only good for one thing.
There you go. That's the row sheet.
They were only able to do. They weren't able to store instructions.
Correct. Okay, so before von Neumann, how you specify the operation of a computer is done by hard wiring. We're talking about connecting from here to here, that from here to here, and so on. So von Neumann's contribution is to store the program, the instructions, what the program or what the computer is supposed to do, also in RAM. So now you have contention, right? Because the same memory that is storing data where you need to get in order to process anything is also storing the instructions. Okay, so now you have more need to access memory. And as a result, if your memory bus is not fast the way it is supposed to, you can have a really fast processor, but why? Because it's not going to get instructions or data to process as quickly as it can. Is that making any sense? Okay. Now there is something in between that we haven't talked about, and I would probably not mention it much. That would be the cache. Okay. Okay. What is cache? Other than cache, right? But what is cache in computer technology in that context?
A queue?
It's not a queue.
It's a memory on the processor.
It's a kind of memory on the processor chip itself. Okay, it's called associative memory. Okay, in other words, it is a way to store most frequently or most recently accessed content locally to the processor. Okay, it's a quick way. Okay, so if you just write to a certain location, the memory chip itself, not the memory, but the processor chip itself keeps a local store of what is supposed to be in that location in memory. Okay, it's kind of like a little post-it to keep track of the most frequent operations. It's like, oh, I just overwrote location 269 with this content. So the next time, if you need to access the same location, like 3 instructions down, you're not going to go all the way to the library just to get a page, because you can recall from your short-term memory, that's your cache, that you just did something to that location. So cache is short-term memory. It can save you an entire trip to the library. And that's why more cache means you can feed the processor faster. Okay, the more recently used instructions and data is still there in memory. Is that making any sense? Okay, so the more core you have, the more ALUs you have on the processor die, the more cache you will need in order to realize the full potential of your processor. How do we populate cache? Now this has to do with burst mode memory access. When you execute an instruction, when you run the program, okay, when you run a normal program, do you think most instructions fly all over the place, or do you think mostly they're sequential? They're mostly sequential. Okay, they're mostly sequential until you get to a branch, a conditional statement. When you get to the end of a loop, when you go back to the beginning of a loop, or when you call a subroutine or return from a subroutine. Those are the times when you're not going to execute the very next instruction. You'll do something else. Are we making any sense? Okay. So the way your cache memory is populated is not byte by byte. It's not 32-bit by 32-bit. It's by burst mode. Okay. So when you use burst mode, you're not reading only one single instruction or one data back. You're reading a whole bunch in anticipation that those are the ones that you will also need later on. And that's when you use DDR2, DDR3, and DDR4 technology to speed up the transfer, because you're saying, I'm not just accessing one location, I'm accessing the next 16, the next 32 locations. And then you put all of those into the cache memory on the processor chip itself, because you're preparing for the next few instructions. Are we doing okay so far? Okay. So now when you write algorithms, okay, when you are thinking about cisp310, okay, you think about all the data structures and stuff like that. Okay. Think about an array. Think about the different sorting algorithms for arrays. Think about quicksort. Do you think quicksort lends itself to this type of technology? In other words, when you access one element in the array, the next few elements are very likely to be needed very soon. Does that apply to quicksort? The answer is nope. Quicksort has no locality. What about merge sort? You guys, okay, how many people know what is merge sort? Okay, so what about merge sort? Does merge sort have any type of locality, especially later in the game? It does, okay? Because you're reading from two different queues and merging those into one, so you do have a lot of locality. So that can have an impact on the actual timing of an algorithm. It doesn't change the time complexity itself, but it will change the constant. Because merge sort will better utilize DDR technology than quicksort. It's not randomized. It's not going here and here and all over the place. It is all sequential access. Are we still doing okay so far with this discussion? Now, this part is obviously not going to be quizzed. Okay, I will not ask questions in the test, but I want to kind of relate what we have just learned here to something that you might have learned already, or something that you will learn, because some of you may not have taken cisp310 and don't know what sorting algorithms are available. Are we doing okay so far or not? Okay. So what we haven't really moved forward much today. All I did was to revisit how to access memory. So what you want to do to prepare for the next class meeting is to read ahead of me. Okay. So what you want to do is to read just a little bit ahead of me. We are at this point pretty much done with memory access or the von Neumann architecture. So the next topic will be the control unit. Okay, so with the control unit, we still talk about the same kind of stuff, instruction fetch, decode, and stuff like that. My processor, actually has all the components. Okay, so you want to at least take a look at the processor, and I wouldn't spend too much time to understand how the whole thing works. Okay, so don't even try that. What you want to do is look at each component. Okay, double click on the ones that can magnify, that can expand. Look at every single component and see if you can understand how each component works. We already talked about what a decoder is. There's a reverse of a decoder. Okay, a multiplexer and a demultiplexer. So look those terms up and figure out those things first, and then we'll talk about what those components are and why do we have registers and so on. All right. Any questions? So in today's lab, there's no real structured instruction. For those of you who want to work on your subtractor, you can work on it in the lab. And remember what I said about the subtractor is easier than the adder. It has fewer components. So for those of you who have not done that part or do not know why I said that, you might want to look at your design and go like, is there any way to reuse a component for two different purposes? Okay, so that's what you need to ask. It is, by the way, it happens in the half subtractor level, not the full subtractor level. All right, so we are running out of time today in the lecture. Please have at least stay beside the roll sheet, and then we'll move over to the lab.